Today's is a very important topic. Today is the third session that we are going to deal with as we dive now from deep learning towards more on NLP side. Okay, so in your previous sessions, Asha ma'am have already taught you really well on all the basic foundations of neural networks. Okay, she started with ANN, artificial neural network. You have seen feed-forward network, feedback propagation, then you dived into image data, where you work with an image data. What type of neural network would you use? CNN. Why so? What is the advantage? What is the advantage of using a CNN for an image data? Because you could go for spatial correlation and reduction in the dimension of the data while you extract all the features out of it and perform any task like classification on it. Okay, so that was in just about usage of CNN. You have already worked on it, you have done exercises on it. Then started with sequential data. What exactly do you understand by sequential data? What do you understand by a sequence? One after another. That means what comes after another or what was previous to the current matters. Could you give me some examples where this matters? Stock predictions, weather forecasting. In our normal day-to-day life also, if you are going for a textbook, can you just take a print of first page and then 90th page? No. Information will be lost, right? So sequence are important in your day-to-day life. So for that, CNN was lagging. It could not work with a sequential data. Okay. So what was introduced to fulfill the task of working with sequential data inside a neural network? What type of neural network was invented? RNN. Could you give me a full form? Why is it called recurrent? It's a neural network. Why is it called recurrent? Ma'am have explained you yesterday this. What difference could you see into the architecture of a normal neural network to the RNN block diagram? Do you remember? Yeah, you are there. Come again? Okay, and apart from that? It was connecting two layers. In a normal ANN, CNN also you were connecting input to hidden to output. Connection of layers was there. Neural network was there. But there was a speciality in RNN, if you could recollect. Very good. So there was a feedback. So there was, a feedback coming from the current output going to the, it is going to the next part of the layer as the previous output. That was helping you to find out the next output. So in that way, sequentiality was maintained. In other words, we could say that the data was now dependent on time steps. Okay, so you would say that if you want to say the output is y of t currently, then the y of t would be dependent on what? X of t minus 1. Okay. So that was the thing which you have learnt in your RNN section of this particular embedded learning session. So now today's session is all about long short term memory. Very beautiful name. Quite curious to understand what is this long short term memory. Okay, so now see, I will explain you about background, definition, need of what is this long short term memory, what is the internal structure. And then in the subsequent classes, we will see a hands-on on LSTM as well. Now, as I explained you, this was about RNN and I was talking on the feedback element that was present inside a RNN. Yes, yesterday you have learnt about this particular block diagram and its expansion also. Madam has very well explained you all the concept relevant to it. Now, till now, you were aware of X of t and Y of t. Normal, denotions. What was X of t? Input. Y of t was output. Here there was another new term which was added to the mathematical calculations. Can you recollect? h of t. Very good. So what is this h of t, or in case h of t minus 1? What is it? H of t. What is the name? Very good. It is hidden state. So what do you understand by hidden state? Why are you telling this as hidden state? So what could you see over there from the diagram? From layer to layer, whatever output that is being, taken, it is internally, hiddenly passed to calculate the next output. So we call that as an intermediate output. So the other name for that is a state. Okay, so that's a hidden state. Now, RNNs, as you all know, process the sequential data where the output of one step is fed as an input to the next step. You are all clear with RNN, right? Yeah. So, what were the problems that RNN was facing? So, we got to know that RNN could work with sequential data. Wherever you come across this word called sequential, you are thinking that it is dependent on time, correct? If I know that I am going to take a previous output and calculate my next output, there should be something to store my previous output. So the moment this word is coming store, that means what is involved? Memory. Yeah? So does CNN has a memory? No. Does RNN has a memory? A bit, yes. Okay? But RNN comes with own challenges. What is RNN? Shall I tell you in short, in the layman's language? It is Ghajini. What is Ghajini? You are all aware? What is that famous thing that is associated with Ghajini? Come again. Short-term memory loss. Okay, short-term memory. So that is RNN. That means short-term memory in the sense what? It may forget if you feed it with a large amount of information. So that was the drawback that RNN was facing. We will dive that into more detail. So what were the challenges? Now technically, layman language is okay? Now technically. So you all know that there is a forward propagation as well as a backward propagation that is happening inside RNN also. So you use gradient descent algorithm, yeah, inside that particular neural network. So now RNN was facing challenges like exploding gradient descent and vanishing gradient descent. Okay, so what is this exploding gradient descent? Where the gradient will grow too large, that will create instability in your model. And there is a way to avoid it by using suitable activation function. I leave it on you to now think and brainstorm what activation function could help. The answer is there in my subsequent slides. I will ask you again. Keep that point in your mind. Which activation function would be suitable to avoid exploding gradient descent? Several activation functions you have studied. Okay. So that is your brainstorming part as of now. Okay. Now second is vanishing gradient descent. Very, very important. Okay. So what is this vanishing gradient descent problem? So as you, what is weight updation formula? You are learning parameter formula. When you apply a gradient descent algorithm, what is this? You always study updated weight equal to old weight minus learning rate into gradient. Correct? So whenever you want to update the weight, see, neural network is all about learning. Neural network is all about updating. That's why you are going for back propagation. You want to update the weights and parameters so as to get a very optimized output. Till then you keep on updating. So you update. How do you update? New parameter or new weight, suppose, is equal to old weight minus whatever speed you want to go with, learning rate, hyperparameter. That is, it's a product, it is multiplied with a gradient. Now, imagine a situation. If gradient is going so low that it is approaching 0. If gradient is approaching 0, then what is going to happen to new weight? New weight is equal to old weight minus learning rate into 0. So what is going to happen now? Old weight is equal to, so what is happening? Are you updating? So are you learning? Learning stops. Understanding. So this was the problem that RNN was facing. Okay, so there were two challenges that RNN faced. One was exploding gradient descent. To somewhat extent it is manageable. Most crucial was vanishing gradient descent, which in which the gradient became very small and learning became very difficult. Now, why RNN failed for long sequences? As I told you, generally in RNN, what is going to happen? The earlier layers of the network don't learn much due to vanishing gradient problem. I'll explain you this. So, from your end, see what is going to happen? This is the input layer, feed forward, output. Back propagation mein what will happen? Output, loss calculation, updating which layer first? Last layer, then second last, then next, then next, so on till, so early layers comes last. So now updation is happening. So as I told, gradient was little bit manageable, learning happened in the outermost layer, then the second outermost layer. Slowly gradient started diminishing to 0. Is learning happening now? Is learning happening now in the innermost layers or the initial layers? No. So RNN, the earlier layers will not learn much because of vanishing gradient problem. So because of this, RNN tends to forget. Because the layers towards the input side, they are not learning. Okay, so RNN forgets and thus have a short-term memory whenever you have got long sequences. For smaller sequences, fair enough, gradient is present, learning is happening. For longer sequences, till the time it comes to the input, the first layer of your network, when vanishing gradient happens and RNN starts forgetting. So you cannot rely on its output. So RNN cannot retain long-term sequences in the memory, and because of this problem, LSTMs were invented or introduced. So LSTMs were introduced and it has a gate mechanism that I will explain you that helps to manage memory and also to work with long sequences more effectively than RNN. So are you clear now why are we studying today LSTM? So what was the drawback of RNN? What happens in vanishing gradient problem? Yes, the early layers cannot learn as gradient approaches 0. Okay, so what was the solution? LSTM. Now, there are few questions, and there's a question that I want to ask. Read out. Answer. Why do you think memory is crucial for handling sequential data? I think I already explained you just now. You have to answer now in your own terms. Tell me, why do you think? Okay, and? Yes, correct. So, next question. What is the difference between recognizing a word and understanding the context of a sentence? Very good. So, understanding context is very important. Giving irrelevant answer is a different scenario. So, when I say understanding context, that means what? I should understand meaning of that sentence, store it somewhere, and then I have to say predict the next word based on the stored meaning or the stored sentence to which I have understood the context of. Clear enough? So this is the requirement of memory. Memory is needed. So RNN was having short-term memory, say 1 sentence, 2 sentences, you will be able to very easily do it. But then when it comes to a huge corpus of data, nowadays we are working with NLP applications that also we are going to see. Okay, lot of data that deals with large amount of text. Then how do we remember that? So memory was the requirement, and recognizing words is straightforward, but understanding the context requires memory of the previous words. This is where you find LSTM excelling. Okay, and thus memory cell is the requirement whenever you want to go for the design. Okay, so understand now. We will now use this term called LSTM cells quite often. Okay, so that means we are now building our memory cells which would be able to retain important parts of your data that you are working with, the sequential data that you are working with, and help you to give your output based on these storage of these long sequences, important data that you are storing through these long sequences. Okay. Now, let us understand it better through this simple example. I don't know how many of you could see it actually. I'll read it for you. If I am using any traditional RNN, that we call it as a vanilla RNN. See, understand, LSTM is not something new out of the box. It is just a more enhanced version of an RNN. Okay, so there are two actually speaking. One is LSTM, another is in GRU. Okay, gated recurrent unit. And our first one is LSTM, GRU. GRU is little bit more complex in architecture when compared to RNN, but both of them can go hand in hand. So now we are diving into LSTM because that is our requirement for our next modules of NLPs. Okay, so if I use a traditional RNN, let us see one simple example of prediction of the next word. Okay, so if I say the sky is dash, what is the answer that an RNN would give me? Sky is blue. Because how big is your sentence? 4 words. It's manageable by an RNN. Okay. Now suppose I take another example. What did I write? Krishna lived in India for 12 years and he loves watching movies and he's a fan of dramas. He is fluent in dash. Predict. Predict. Krishna lived in India for 12 years. And he loves watching movies. He is a fan of dramas. He is fluent in dash. Hindi. Because for this you will have to remember what? India. Agreed. So, but if I give the same data as an input to RNN, it will not remember India. So, it does not know the context. It will be giving you wrong predictions. Understanding? Okay. So, this is where LSTM comes into picture. That's the reason today we are going to study about LSTM. Okay. Now, reason of failure for RNN was long-term sequences in the previous example, and there was inherent relationship between each and every sentence. So, that's what I was talking on. Context. Okay. Now, what is the solution? LSTM. Now, another question. Read out. Good for you. So, how do you determine to buy something online these days? Check the price. Quality. How do you know what quality? There's only a photo there uploaded. Rating. And I am the person who go by reviews. So now reviews will be like this big. When I read, when I click something on Amazon, it's too big. What do I have that first sentence over there? There's a gist of this review, or in that review, what do I scan for? What do you scan for normally? You do a lot of online shopping. What do you scan for? Excellent, good, amazing. You don't want like poor. Even you can see the quality being poor, not worth buying. Your eyes actually forget about everything and then, scan these words. Yes or no? Yeah. So, if I suppose buying for anything, I would look for say amazing, I will definitely buy it again, very good quality, etc., etc. So, you will subconsciously remember important points like this. Say if you're talking on say positive thing or negative thing, whatever. But important point, relevant to the product that you are buying. Yeah. Now, what are the words that you will not concentrate much on? It, the, a, and. Yes or no? Yes or no? You just throw it away. You just don't even want to watch them also. Correct. So now, when recalled, you would remember all the keywords and tell the feedback. Yes or no? Say you went for a movie. You saw the review online and you went and you would say your friend, did you say, cut to cut what was in the review? No. You would say some important key points that were there. Correct. So that is what is LSTM doing. Okay. Long, short-term memory. So long-term mein, it is going to store these keywords that would help you with the context of that particular text that you have scanned through. And it would be helpful in predicting whatever output that you are going to, predict next. Next word, let's say. Okay, so are you clear now? So how you have scanned and how you have omitted some things, the same way LSTM also works. So when I am telling long-term memory, I am not telling entire thing it will be able to retain into its memory cell. It will be able to retain certain keywords. Like just now in this example you have seen. Clear enough, guys? Yeah. So now, what is the need for LSTM? So, till now we have seen what was the need for LSTM. It's clear, right? Now technically we will see how you can achieve, how you can satisfy this particular need. What is the need? You have to retain certain keywords for a longer duration of time. That is the need for LSTM, right? So how does it do that? It has gates inside it. So now I am using this word called LSTM cell. Okay? So there is an LSTM cell. Inside it there is a gate. What is the normal functionality of a gate? Why do you have a gate? To allow somebody coming in or going out. So the same thing is happening over here. The flow of information could be controlled or regulated through these particular gates which are present inside the LSTM cell. It also understands within the, the input that you are introducing, which particular word is of higher importance and priority, like keywords. Okay, and then it is going to retain it. Which one is of lower priority, it is going to discard. Clear enough? Next, uses the relevant information to make the prediction. So it understands the context and then gives you the, the next word inside the prediction or whatsoever application that you are going to use it for. Clear enough, guys? Yeah? Now, briefly speaking, all these that you are learning now in the upcoming sessions and all, they are all a part of a field that we call it as NLP. Idea about NLP? No full forms. Even I know full form. Natural language processing, but see, it's just a bad joke. But what do you know about NLP? Yeah. You are giving me applications. I will teach you about applications, but in your words, we need not have any bookish definition here. What do you understand by natural language processing? Processing the human language. Okay. So it's difficult. Okay. There are many places in the English where if you can just change a comma, the entire context changes. The movie was good, not bad. Yeah, movie was not good, but bad. A single change in the word changed the entire sentiment associated with that particular sentence. The movie was good, not bad. What review? Positive review. The movie was not good, comma, bad. Same words, just a change in the position, positive became. So that's what is a natural language in any other language whatsoever it is. Okay, so we are trying to understand a natural language. We know as a human, we understand things. This is like a super supercomputer. But for machine, you're training. So that's the reason you're learning. You're learning natural language processing. I'm not diving much into deep. I'm going to explain you only those parts that we are going to take it further. Okay, so NLP applications that you use in your day-to-day life, there are many. You know it or you don't know it, but actually you are using. Probably your mother or your grandmother don't even know about, NLP, but when they are using their Microsoft Word, they are doing this autocorrect option. Whenever they are using their WhatsApp, they are using this autocorrect option. Whenever they are using this Google browsing, they are going for next word prediction, but they all don't know that exactly this is natural language processing. Okay, so spelling correction. This feature of Microsoft Word, everybody knows it. Wherever there is a mistype, you can actually, you can go for it? You can correct that. Correct. Next, machine translation. Very popular these days, no? If you take it to another, say 2 years back also, Google never used to give the next word prediction also. We had to type the entire thing that, you wanted. You all are aware, I'm sure. Now, to whatever you are typing, you are getting that in your whatever mother language, mother tongue you have, you just select it, Telugu, Tamil, Bengali, whatever. It's just giving you in those fractions of seconds. So how is it possible? Through NLP, right? Next, chatbots. Everywhere, even KMIT has its Sarathi, right? So chatbot is like based on your input that you are giving, it is trying to understand the context of those questions and trying to give answers from its database that it has got. So how is it? It is again the most popular application I can say of NLP. Okay, every simple app nowadays on mobile has got a chatbot. Nothing works without it. Yeah. Then, as I just gave one example, sentiment analysis. Sentiment analysis in the sense, you understand if that sentence was positive or negative. Where would you use these? Opinion mining or sentiment analysis? Reviews. Shopping experiences. Movie buffs. And any service that you would like to take, especially when you are investing some money into it. Yeah. So those are places you would be requiring your opinion mining. You understand and analyze the attitude, behavior and the emotional state there. Okay. And here it is implemented with a combination of NLP and through the statistics as well, wherein you assign the values to the text and identify the mood of the text. Clear enough? Happy sentence, sad sentence, classification, positive review, negative review, good experience, bad experience. Okay, so like that, you try to understand what that sentence actually holds, what expression or mood that particular sentence has got. So that is sentiment analysis. In future, you would be doing a lot of projects based on, these concepts. Very, very easy. You never knew that actually this was NLP. Somebody sends you an important mail and you are not seeing an inbox and the other person tells, what does he tell? Spam mein dekho. Yes or no? Yes or no? So this is automated, no? Spam is not in your control, no? So what is this spamming and not spamming? It is also an application of NLP. So how do you think spamming and non-spamming happening? How are you classifying? Classification task, typical classification task. What is going to happen there now? It reads the entire text of your mail that has come and understand if it is relevant or irrelevant, and then places that in your spam box or your inbox. Clear enough? What is this? Very, very important for you people. Last minute exam batting. Yes or no? Yes or no? Yes. So what do? Don't you do this with ChatGPT? Text summarization. Last minute, who wants to study that big PDF that she has sent? Just enroll, take some raw data, important data, mug up and give the answer. That's what you do? Yes or no? Okay, so this is also one of the major applications that you could see. Now, what is common amongst all these applications that I have explained to you? What are applications I told you? Recollect. It's not a monotonous session. I feel bored. You have to talk to me. Huh? Huh? Translations. Huh? Okay. Huh. So what was common in say these 3 or 4 applications that you told? Huh, very good. So entirely everything was dependent on input as a and context. How the words are interconnected to each other. I gave you that explanation. No? The movie was good, not bad. The movie was not good, but bad. So just a little change here and there, the entire sentiment got changed. Hai na? So we are trying to understand the interconnection between these words, the context that it is going to give you, and then you are going to use it for several applications. So now what did you understand? I said okay, positioning matters. I said okay, context matters. Then RNN matters. Building the model, no? Yes, of course you are going to build that model. Sentiment analysis model for an example. RNN matters. Think and tell. Remember the context. Use your super LSTMs. Huh? RNN now, does it matter? Yes or no? How many of you say yes? How many of you say yes? Yes, RNN we will use here. How many of you say no? The first thing is you should ask me, madam, how much is the input that you are giving? Long sentences means LSTMs. Long sequences of sentences, if it is, you will be using LSTMs. Clear enough? So, LSTMs you are going to use majorly in almost all NLP applications building. Okay? So, sequential data whenever you are working, from now we will be using LSTM. Okay? What is the disadvantage of a normal RNN? Vanilla RNN? Vanishing and exploding gradient. In a layman language, short-term memory. It could not retain what? Long sequences of data. So if you are working with a long sequence of data, you would be using LSTM. Okay. Now, LSTM stands for long short-term memory, which is an artificial recurrent neural network only, but an enhanced version of it. Okay, and it is used in the field of deep learning. This was invented in the year of 1997 by Sepp Hochritter and Jürgen Schmidt-Huber. Unlike standard feed-forward neural network, LSTM has got feedback connections, which was also a part of your normal RNN that you have seen. Right. It can process not only single data points, but also entire sequence of data. So whenever suppose you are going for video captioning, then at that point you will also be using LSTMs. Okay, so it's like sequence of images there. That is also a sequence data. You would use a combo, but of course, of RNN using LSTM and a CNN as well. But I'm just giving you a simple application where you can combine these LSTMs or enhance RNNs and achieve something in good, better applications. Okay, so it can not only process single data points but also the entire sequences of the data. That's why it's important for us now to learn about LSTMs. Now, diving now into little technicalities. Okay, overview is clear. What is drawback of RNN? How did we come to LSTM? Where is LSTM being utilized? Clear enough? Now diving into technicalities. So we will now see about internal structures of LSTM. So we will discuss this definitely in detail in our subsequent slides. As of now, a little gist. You could actually ask me, ma'am, how is it possible that it understands which keyword? Because I told it is not going to store the entire sentence. It is going to, to store the keywords. How is it retaining keywords? Then how is it processing the next sequence? Same like RNN. So I would say the structure internally, as I say, the memory cell or an LSTM cell is designed in such a way that it has got its gates inside it, which is going to control the flow. So if I talk on gates, there are 3 types of gates which we'll study in detail about their architecture. Input gates, it is going to control what information you're going to give as an input or to be added. Forget gate, what all words that are useless to you, which you can forget. And output gate controls the information that is coming as an output from that particular memory cell. So as of now, a brief as a black box module LSTM cell is clear with you? Yeah? Now, talking on hidden state. RNN, you have learnt about hidden state. Yes or no? What does a hidden state do? What does a hidden state help in? Yeah. Okay. So you are aware of it. So here, LSTM also maintains a hidden state which acts as a short-term memory of the network. So same as RNN. Okay. There's a hidden state that is taking the current output, gives us an input to your next time step, helps in calculating its output, creating a very short memory over there. Yes or no? Yeah. So that short memory is here in LSTM. The name, what is the name? Long short-term memory. So the short-term memory is a part of RNN only. That's why I told it is an enhanced version of recurrent neural network. It's not completely new. So that short-term memory part we are retaining as it is. Clear enough? So hidden state is present which acts as a short-term memory, and this hidden state is based upon the input, the previous hidden state and the memory cells, current state, same as your RNN phenomena, same thing. Now, what happens to the long-term memory? Okay, there's this word long and short-term memory. Short-term memory, same as RNN, hidden state. Long-term memory. Can anybody think about it? Structure is there. I will explain you. Any predictions? Important keywords have to be retained. That will be returned in long-term memory. So keep this to you. Take it brainstorming. I am going to the next slides where I will be again asking you this question. Now, and I think you will be answering till that time. Now, first we will understand a simple process, how RNN and LSTM work very, very simply. So, before going to the actual architecture and diving into that part, we will see the simple working of these RNN cells and LSTM cells. So, suppose if I am taking RNN first, I am not excluding RNN here because that mechanism of RNN is still utilized in LSTM. Okay. So, now what is happening here? The words get transformed into machine readable vectors. What do you understand by that first? Whatever words or the text data that you are giving as an input to your particular model, you are trying to first convert that as vectors. Why? Very good. Because machine understands only mathematical values. It cannot understand your language. You are making the machine understand your language. Yeah. So for that you are trying to convert. Okay, agreed. So you can see this box of cereal gave me a perfectly balanced breakfast. Whatever one word, it went to one cell and then immediately it got converted into its vectors. Okay. Now, what do? We take that particular sentence, you normalize it and then you vectorize it and then you try to use it in your model. That's the typical text pre-processing workflow that you follow in any model of RNN, LSTM or GRE or any NLP model. Okay. So you take those words, scraping that we call it, data will be scraped, labeled, normalized if it is not, and then vectorized. That part is very important for us now to understand what is this vectorization, and then you use it inside your model. That's a typical workflow of text pre-processing. Today we will do an exercise on text pre-processing. Before going to that, ever heard about this word embeddings? Ever used, ever heard? Anybody? Embed. Word embedding. Embedding layer. Till now you are familiar with convolution layer, pooling layer, dropout layer, etc. etc. है ना? This is new word for you. Huh? So embedding layer you will hear in RNN, LSTMs or majorly NLP models, wherein you take your corpus of data, you try to convert that into machine readable vector form. So the entire network that is actually doing this for you is one separate layer that we treat, and we call it as an embedding layer. That is the heart and soul of your sequential network here. Are you clear? So what are these word embeddings? It actually gives you these timestamps that you are actually working on. Okay, so word generated on each timestamp is a character, not a numerical value. Yes, of course, right? If I am giving KMIT, it is not a number. KMIT, these are all characters. So neural network cannot process string data, you are all aware of. And conversion of words or characters into numerical values is very critical point in neural network applications like natural language processing, wherein your input is entirely what? Text, maximum amount of time. Okay, so word embeddings are a way to represent these words as dense, continuous valued vectors in a fixed dimensional space. So it's important. Abhi, for an example, in a normal neural network, like how learning rate was a hyperparameter that could affect your model indirectly. Here, choosing what length of vector that you are giving for every word is a hyperparameter. So it's very important for you to understand this word embedding. Okay, clear enough? Now, there are different types of representations when you want to represent a particular word into its vector. Very simple is space representation, one hot encoding. How many of you are aware? One hot encoding? So, okay, majorly. So, one hot encoding, what is the problem? Suppose if I say the movie was good. How many words? 4 words. Easily processed using one hot encoding. I write 2 pages movie review. You can't go for one hot encoding. Why? Because one hot encoding is a space representation. It is a high dimensional and extremely sparse representation vector with a large amount of positions as zeros. You remember one hot encoding? Significant position is given as 1, but that position will not be repeated for another word. Unique position for a unique word. But how many such words are there? That much should be the length of your vector to give a unique positioning to 1 every single time you come across a word. Clear enough? So as your data is increasing, the length of your vector will also increase. Of course, the computation problem, speed in computation and computation time will be more. Yeah. So it is computationally expensive. The speed will slow down. Time taken to compute will increase. And also, it is not conducive to neural network training. It ignores semantic relevance inherent in the word. So what is this semantic inherence? I told you, I gave you an example of a review of a breakfast cereal. Hai na? So what did I see? Did I go through the entire review? No. What did I scan for? Keywords. What did I ignore? The and all irrelevant information. Can you do that here? How many words are there? That much amount of length. And suppose if there are certain words that are repeating more frequently, then and there are certain words, if they are less frequently used, then also you have to use that fixed length of vector. Yes or no? So, what is the strategy to improvise our computation? Scan for the words which are more relevant, scan for the words which you use more frequently, and then assign a short length vector to it. That means, you make your vector length to be dynamic enough. Your mind will think in all those directions. So that is not possible with space representation or one-hot encoding. That's why we don't use it generally. Okay. Next is dense representation, which is embedding. So what we go for? We go for semantic relevance here in word embedding.
Process will now be like a lookup table, wherein you will fetch for a particular word what is its dimension vector. Clear enough, guys? So this is how things work, and two simple processes only I am explaining. Remaining all text processing today I will explain while I am doing the exercise. So it is like input tokenization and embedding lookup. Okay, are you clear with the process? Let's see, understand it better with an example. For an example, if here I have taken a very small sentence called I am happy. So first step is what? Tokenization. So what is happening in tokenization? The very first thing, you create a unique words that are present
inside your given data set. So what are those unique words there? Non-repeated words. Okay, unique word means I am happy. You could see there. And then after that, input tokenization mein what is the next step? Allot indices. What are the indices that are allotted there? I 0, am 1, happy 2. So what is the range of index? 0 to 2, because there are 3 words. Clear enough? So determine number of words. Index range should be 0 to number of words minus 1. Clear enough? Now it will be tokenized into 0, 1, 2. So instead of now using that sentence as I am happy inside my network or a model, I am going to use 0, 1, 2. 0, lookup table, what is 0? I. 2, what is 2? Happy. Understood. That's how again it will be remapped. Clear enough? Now, for a vocabulary of let us say 10,000 words given, for a vocabulary of let us say 10,000 words that are given, assume as a user I have chosen my embedding size as 100. Okay? And then what would be the embedding matrix dimension? What would be the embedding matrix dimension? How many rows, how many columns? 10,000 by 100. Remember that. Number of rows would be equivalent to the number of words that are present. They will be of, the columns would be the, the length that you have selected as that of for your vector, the vector dimension. Are you clear? So embedded matrix dimension would be what? Would be what? 10,000 by 100. Okay. So now the word happy, for an example, what is the index? So how am I calling that inside my LSTM? Am I calling that as happy? What am I calling? Embedding of. So after you have embedded, you have given the index as 2 to happy. So wherever you are working with happy, it is actually embedding of 2. And whatever weights that you have associated inside its vector dimension. Are you clear enough? Longer run, you will also see that high priority words will be given shorter vector lengths. Low priority words can be given longer. That we are not working on still, but I am telling. Why? To enhance your computation efficiency. Because if the word is high priority and it is being frequently used, wastage of, that much computation taking a vector length so big, say 100, you can actually reduce it. You can actually impart dynamism in giving the vector length. That is actually the basic thing, but I'm just giving you an overview. So right now you are understanding why do you want to embed, why it is easy to have a lookup table, and why you should keep your vector length dimension, thinking, You have to very much be very specific how much length of a vector that you are going to give. That is going to affect your computation. Okay, and then finally, what is the dimension of your embedding matrix? Clear enough, guys? If this is clear only, we can go to the next one. Clear? So now from here, the entire text that you have given as an input will be first tokenized, will be indexed, will be created with a vector, and then can be given to any model like RNN or LSTM. RNN also same way. Okay. Now, as I told you, embedding vectors can be randomly initialized. This was one simple sentence. I am happy. I could create 3 vectors, generate by my own. I can randomly initialize. What about huge corpus of data? No? These days, you have humongous amount of data across the web. How do you do that? It's difficult for me to create an embedding layer on my own from scratch. Hai na? So for that you will use pre-trained, embeddings. You might have heard about Word to Vec. Ever heard? Okay. So these are all like pre-trained embeddings. You are just invoking that, taking ready-made vectors. You don't want to create those vectors again. So you just invoke that Word to Vec or Glove and then you get your vectors. Simply use them in your model. Clear enough? So there are many like Word to Vec, Fast Text, Glove, etc. As I already discussed, embedding size is a hyperparameter. Larger dimension will capture more information, but it will affect the computation, because as you are increasing vector length, you are increasing mathematical calculations also throughout in your model. So hyperparameter it is. You have to be mindful about what are you giving as an embedding size. Clear enough? Next, input to an embedding layer is a batch of sentences with indices, as I explained. Output, be careful with this. You will be whenever you will be doing the next subsequent exercises, you will be working on with an output which comes as a 3-dimensional tensor, wherein you have sequence length, embedding dimension. Now you will also have batch, because you are working with huge amount of data later, batch wise. Okay. Next is, for an example, if you have 2 batches, batch size of 2, sequence length is say 4, embedding size you are giving it into a vector of say 100 dimensions, then your output would be 2 by 4 by 100 tensor. Clear enough? You have to understand these things to analyze any code for RNN or LSTM. Because eventually text cannot be understood by a machine. You have to make the machine understand the text. And that is done through word embeddings that you have seen just now. Clear enough? Yeah? Now, embedding layer is trainable. It learns to assign optimal vector representation to words during the model training by initial embedding matrix. You can do it on your own by randomly generating it, or you can use any pre-trained embeddings like Word to Vec or Glove, etc. to get that. Second, you will train with a loss function. For an example, if you are training for sentiment analysis, the model will adjust the embeddings to better separate positive words and negative words. Also, you will undergo gradient updates. During backpropagation, embedding vectors are updated along with the model weight. So now you are understanding how it is a hyperparameter. Till now, whenever you have done the backpropagation, you would adjust only weights and biases. Here it is possible to adjust the embedding vectors. The better the embedding vectors, the better will be your prediction about any NLP task that you are doing. Clear enough? Why did we study embedding, word embeddings? Okay, and how is it functioning? Okay. Now, simple process where I began from. I told you word embeddings will be common for any architecture like RNN or LSTM. It will be like a pre-step towards going to any model. It could be a simple RNN model or an enhanced LSTM version of it. Okay. Word embeddings remains the same. Fine. Now, simple process. As I told you, given the word, assign it to the RNN cell, say example, and then that using a word embedding, it will be converted into vector. Till now, we saw that mechanism, how it was converted into the vector. Now again going back to the process. So, the sequence of the words are processed one by one, wherein the previous hidden state is passed to the next step of sequence. This you have studied in your RNN. Now, let's see how a hidden state is calculated. I am explaining this because I told you that LSTM has got that short-term memory coming from this particular mechanism only. Long-term memory, we have to still think about it. Okay. So, short-term memory mein, how it is coming? It is coming through this hidden state. A vector with a current input and previous input is created and it is passed through a tanh activation function. I asked you one question in beginning. Do you remember? How can, I told you how can you, work or how can you overcome a vanishing gradient descent? I told you how can you overcome vanishing gradient descent in RNN by using LSTM, by enhancing it through LSTM. I asked you one question. How would you overcome exploding gradient descent? I told you I'll ask you later. You think about it. So this is the answer towards here. Here is the answer. Can you figure it out? Very good. So using tanh activation function, you would be able to curb exploding gradient descent problem. How? Very good. So tanh activation function actually regulates its output between -1 to 1. So why tanh is an important function? Because it's a squishing function which helps you to regulate the value between -1 and 1, thereby reducing the explosion of gradient descent. Now, information vectors undergo various mathematical transformation in its process. Some values can explode in this process. Yeah, come back. Some values can explode in this process, causing other values to be insignificant. Therefore, a tanh function will ensure that all the values maintain between -1 and +1. If that is the case, there is no chance of explosion of gradient descent. They will be curbed down between -1 and 1 and that problem can be sorted. So, exploding gradient descent you can overcome in RNN also by allotting a suitable tanh function, but RNN still cannot overcome short-term memory loss problem. For that you have to go for LSTM, there is no other option. Now, let us see LSTM that I was discussing. It has a similar control flow as that of RSTM. It also processes the data sequentially, passing on the information as it propagates forward. The major difference lies in the operation within the cells of LSTM. Now we are coming towards the major part of this particular topic, how this long-term memory is created. Short-term memory is similar to what hidden state is carried out through RNN. Okay. Now, how are we creating this long-term memory? First problem is solved, exploding gradient descent. Second problem we are going to solve now. Now, what makes LSTM special? You have learnt it throughout. It can achieve long-term dependency. It knows which information to discard or retain. How does it achieve it? How does it achieve?
Repetition.
Repetition of what?
Similar words in one context.
Not repetition, storing.
Memory.
Memory. And? Okay. So, let's see. Internal structure if I talk on, it has two important parts. The cells of the LSTM is designed in such a way that it is able to retain some important keywords from the past sequences. Not all. Important keywords it is going to store inside its cell from the previous sequences. Also, its architecture has got gates that will help you to regulate information. Regulation in the sense, which information is useless and you can discard, which information is good and which can be taken forward, which information to be updated to the previously existing information so that it helps in the prediction of your output, whatever it is. Clear enough? So all of these things will be controlled by the gate mechanism. So LSTM architecture has a chain structure that contains 4 neural networks and different memory blocks called as cells. Information is retained by the cells and the memory manipulations are done by gates. Are you clear now how this long-term memory we are able to achieve? So it's not exactly long-term memory. I am telling important parts of the keywords will be retained throughout till you predict your output. Thus the name comes as long short-term memory. Still short-term memory because you are discarding or forgetting whatever information is irrelevant. Relevant information, you are keeping it for a longer duration of time, which helps in the prediction of your output. That's how the name falls as what? Long short-term memory. So you understand one thing. When I am telling your short-term memory, definitely there will be a hidden state. When I am telling a long-term memory, there has to be some other thing that is going to take care of it. Yes or no? Yeah. So this is how an LSTM cell looks like. Can you figure out what are the things that are present? Then we dive more into detail. Analyze the figure. What you could observe. You are able to see 4 things. I explained 3 things as gates. What are the 4 things? Read. Input gate, output gate, forget gate. What is it? So what is this cell state? What is this cell state? That is your memory highway. That exactly is giving you a long-term dependency on the important keywords that are present in your sequences. Clear enough? We will see each of them in detail. So before I actually go into detail of each of them, first what is cell state? As I explained, cell state acts like a sequence highway which transfers the relative information down the sequence chain. Okay? And it is like the memory of the network. That means this is long-term memory. And your internal, that is short-term memory, wherein you are discarding few things, keeping relevant thing. Where are you keeping that relevant thing? That long-term thing is actually given by your cell state. Okay? But of course it helps you to determine your output also. Okay? Cell state can transform information from previous time steps as well. Thus it reduces the effect of short-term memory. Information can be added or removed via the gates which are present in the cell. Gates. See, what are these gates? They are also neural networks. Okay, just like a block diagram I have represented there, but internally they are also neural network. What you do is just you would invoke forget gate as a module, but what is it inside? It is a neural network. Okay, trained to work like a forget gate. Okay. So, gates are a kind of neural networks which decide which information to retain or discard on cell state. Gates are trained to learn which information you would be taking further or which information you would be discarding. Clear enough? Hidden state of an LSTM if I am talking, hidden state is of 2 parts. One is a normal hidden state like an RNN. One is a cell state. Cell state we call as an internal memory where all the information is stored overall. Okay, previous time steps ka important keywords are also stored. Hidden state is used for computing your next output. Okay, cell state and hidden states are shared across every time step inside an LSTM architecture. Okay. Gates, if I talk about, every gate you could see there is associated with one activation function called sigmoid. What is the range of sigmoid function? So what do you understand by 0 and 1 in a normal layman language? On or off. It is there or it is not there. So now you are understanding why sigmoid is important, where tan h is important. Okay, where you want the data to be calculated and then squished to a certain value, you will be using tan h. Where you want data to discard, where you want data to keep, there you will go for a sigmoid. Architecture also you should be able to analyze where we are using what type of activation function. Clear enough? Now, sigmoid function squishes the value between 0 and 1. It helps you to either update the date or update the gate or to forget that particular data through that particular gate that you're working. You want this keyword, let's say amazing. Amazing is a positive word through its semantic relevance. So yes, it has to be kept. So will you forget it or will you retain it? Retain it and give it further for prediction. Okay. Now, there are 3 different gates which regulate the information flow in an LSTM cells. The first one is a forget gate. The forget gate, you will decide, this is also a sigmoid layer because you will decide which information you want to forget, which information you want to keep. I am happy. What is the important information that you would like to keep here? What you would discard? So, taken a word I, you will think to, the LSTM thinks is trained to think discarding or keeping. Discarding, forget gate output will be 0. Forget. FT will be 0. Whatever word is coming, multiply it with 0, it will be forgotten. Whatever word is coming, multiply it with 1, it will be retained. Getting it? Getting it, the process. So, it looks at the previous hidden state ht minus 1 and xt. What is ht minus 1? Previous hidden state. Xt is the current input word that you are giving, and it will be multiplied with the forget gate output in your future coming block diagram that I am going to show to understand if that current particular word will be forget or it will be retained. Let's say we are training an LSTM to predict the next word in a conversation, and here's the dialogue. Hi, my name is Alice and I love to play. So in this case, the forget gate might forget the greeting. Hi, my name is, and it would like to keep Alice and the next important words that are present. So this is the forget gate equation, and that is the block that is being shown over there highlighted that works as a forget gate inside an LSTM cell. So what is inside the LSTM forget gate equation? Input word xt, previous hidden state ht minus 1, and what is the mathematical activation function that you are giving it to? Sigmoid. Why sigmoid? If the sigmoid output is 0, ft will be 0. Ft is the output that we are writing out of the forget gate. That means this particular word is decided to be forgotten. This particular word is decided to be retained. 0 and 1. Clear enough? Next is input gate. Okay. So what is happening inside an input gate? You will decide how much of new information is to be added. I told, hi, I am Alice. I would like to play. Play dash. There's a prediction. Okay. So, hi, I am discarded. What is retained? Alice. I would love. I and would discarded. Love. Loving, hating, again a sentiment. Important. Okay. So, what is the next word that has to be appended? Love. Next, play is also important. You cannot discard. So, Alice, love, play, and then you will predict whatever it is next. Okay. So, in this case, the current input is play, and the input gate evaluate how relevant it is for updating the memory. LSTM already has the phrase Alice and I love to play stored. The word play is useful because it tells the model that Alice is probably talking about a particular hobby or activity. So that would be your next prediction. What does Alice would love to play? It could be cricket, soccer, guitar, anything. That would be your prediction. Okay. So the input gate adjusts the memory by adding more detailed information about what Alice loves to do, perhaps by focusing on the verb or the activity that has been given throughout your data. Okay. Now coming to the mathematical part again. Input gate में the next step is to decide what information is going to get stored. Okay. So first what is going to happen? Sigmoid layer called input gate layer decide which value we will update. There is also a tanh layer here inside this input gate. So there are two activations that we are using in an input gate. One is a sigmoid, another is a tanh. So sigmoid will decide which value to update, and tanh will create a vector of this new candidate that is supposed to get added. Clear enough? Candidate state. Okay, so now you have got IT, which is going to decide which word to be, you are going to update, and C dash of T, if I can say, then that is the new candidate value that you are going to add to your cell state, because cell state is carrying long-term memory. This is an important word that has to be updated to your long-term memory, so you require C dash T there. Clear enough? So you will be using two activations, sigmoid and tanh. So for an example, pardon me for that. For an example, if I would like to say, Mark loves to sing, he is a good singer. Jacob loves to sing too. So now Mark is going to be replaced with Jacob. So here now what you have to do now, give a separate input now. In place of Mark, you have to now add Jacob as the subject. Are you understanding? That's why a sigmoid, for the appension, you would be using a tanh. Okay. So now it's time to update the old cell state CT-1 into a new cell state CT. So you can see over there what you are doing. After you have calculated C dash T and IT, both of them are multiplied and added to your main cell state, which is on the top, which is serving as your long-term memory. Clear enough? Little difficult with your mathematical calculation, but at least try to an extent where you can understand what is forget gate doing, what is input gate doing. You are not going to build them through scratch, but understanding is important internally so that you know how they are forgetting, how important information is added, how unused information is discarded. Clear enough? Now, for what is the last gate that you have got? Output gate. So finally what is happening in the output gate? We decide what we are going to output, and it will be based on the cell state, but a filtered version of cell state. So you could ask me that question. Input gate mein you have given sigmoid, you have given tanh, you got two outputs, IT and C dash of T. That same C dash of T you can use to predict output, no? I can't directly take output from there. I have to filter that and take that as an output. That's why I should require another neural network, which is an output gate, which does that task for me. So first we run a sigmoid layer on it, which decides which part of the cell state we are going to take as an output. Clear enough? So this is your output gate over there. We put the cell state through tanh function and multiply it with the output of sigmoid gate so that we get only the output parts that we are going to decide to. So let us see a quick example over here. The output gate determines what part of updated cell state should be sent as our hidden state, which will influence our prediction of our next word, that is our application as an example that we have taken. So after the forget gate has decided which information to forget, the input gate has updated the memory, the output gate will look at the current state of memory and it will decide which part to output. So the output gate focuses on the most relevant part. What is it? Alice loves play. Playing what? It could be a hobby. So it is like a prediction. Okay. So the model can predict your next word like a guitar, soccer, chess, any hobby. Again, if the prediction is wrong, what will happen? Alice can play guitar, Alice can play soccer, Alice can play chess. हाँ, क्या करोगे? You will calculate loss functions for that. You will back propagate for that. You can also change your embedding layer for that. And so that you can, give better predictions. You are training, predicting, same like your neural network, but now with a text data. Clear enough? And one more hyperparameter is introduced. What is it? Embedding size. So how well you are training, how good are your vectors, based on that also lot of your predictions will be dependent on. So this is one such application where you are predicting next word as an output. So in Alice, hi, I am Alice, I love to play. So hi, I am got discarded because of forget get. Alice taken as an input, updated to cell state memory, gone to the next word, I discarded, did not append, okay. Love, semantically relevant, appended to cell state. Alice loves is now in the memory. Play also comes. Output has to be predicted. You are writing a code for next word prediction. Alice love play. Think. Predict the output. What it could be. Correct output, 100% prediction. Little low, accuracy is low, loss is more. Go back, adjust things. Clear enough? Clear enough? Functioning. Okay. So, LSTM theory is over. Okay. So, you now understood how we have come from a basic neural network to a specialized neural network that is working with text data or a sequentially dependent data. Mechanism is a bit complicated, but at least a good grip on understanding helps you a lot while understanding exercise. Today's exercise is like text pre-processing and word embeddings using PyTorch. So I have explained you 2 steps for word embeddings. 2 steps, huh? What were they?
See a few more steps that are involved in text pre-processing. So what we call it as a text pre-processing. Thus, text pre-processing and word embedding is the basic prerequisite to any sequential learning model. It can be an RNN model, it can be an LSTM model, it can be a GRU model. Are you clear? So if you understand this, basically you can work with any type of sequential learning model which is involving text as its input. Okay, so I was explaining you how you would convert a particular word into a vector, why it is important to understand that matrix dimension and everything, right? So that we are going to see how exactly this particular NLP model do that, the word embeddings. Okay, so today's exercise is based on that. Try to listen this exercise carefully because based on this only you will be doing one more
tomorrow in your hands-on sessions. Okay, so our learning objective through this particular exercise is to understand text pre-processing techniques like the first one you are aware, na? I explained you. What is it? Tokenization. What is the next one? Lowercasing. What is lowercasing? Converting from uppercase or mixed case into lowercase. Okay? Why it is important? Why it is important? Case sensitivity. Okay, so if you are using KMIT all caps, using 1K caps and all smalls, everything is treated as a different thing. So you have case sensitivity present. So to avoid that, we try to filter it out using lowercasing. That is one application. Next is that is one more technique. Then next is lemmatization. Any idea on this? You are new to it, right? Tokenization, you are clear? I explained. What are you doing in tokenization? Number of words that you are getting, you are converting that into an index, numerical index. That is tokenization. Lowercasing, to avoid any case sensitivity, you are going for lowercasing. Third one is lemmatization. Lemmatization is an integral part of pre-processing inside any NLP application. Lemmatization mein, it will try to figure out root word of any existing word inside your corpus. Okay, for example, learning. What is the root word? Learn. Understand? So it tries to figure out root word without any significance given to the context of it. Okay, we will see all of them. Okay, the next one is stemming. Stemming means like fascinates, fascinate, fascinates, fascinating. So those, suffixes, you are going to truncate them off. That is stemming. Okay, so all of these are your pre-processing techniques involved. So given any exercise and asked for any pre-processing technique, you should be in a position to write the code for it and do that pre-processing. Okay, next is filtering stop words. Okay, filtering stop words, assigning word indices and basics of word embeddings. All of these step by step we are going to see through an example. Okay, clear enough, right? Now the first thing before you start any exercises, taking up your data. So the first step would be data preparation, for which of course the very major step would be to import all the required libraries that you want to function with. So here what are we going to import? We are going to import libraries from PyTorch, which are going to be helpful for us to work with text data. Okay, so what am I importing there? I am importing Torch, I am importing NN, neural network, because that's what I am going to work with. I am importing optimizer and I am also importing string. Okay, fine. Now, you define the paragraph, whatever corpus or text that you want to take for your pre-processing. So there's this major paragraph, a big one that we have taken, starts with machine learning is fascinating, it allows computer to learn from data, so on, till predictive modeling helps in forecasting future trends. So as you look into this particular text that we've taken as an input, you can find many present continuous tenses, many present tenses, okay. You can find some irrelevant words which are of no use like a, the, is. You can find some keywords inside it. You can see some of the words where you can find root word out of it like learning ka, learn. So many things should come into your picture as soon as you see your text. So we are going to take this text. So like this in an exercise, you will be given certain text where you would like to start with pre-processing. So I am going to quickly tell you step by step what are you going to do. So first is taking the data. First is importing library and then taking the data, defining your data. Then the first one that I am going to take care about here is tokenization. So what is tokenization? I have already explained you. It is the process of breaking down a larger body of text such as a paragraph, sentence or a document into the smaller units that we call them as tokens. So the very first process is change the entire sequential data into set of tokens. Clear enough? Now, word level tokenization splits the text into individual words. For example, if I take the sentence, the quick brown fox, it is going to divide into how many tokens? 4. The is one token, quick is another, brown is another, fox is another. So you are breaking down your given data into tokens. Now we will write a code for it. So what are we going to do? Tokenization and lower casing I am doing simultaneously. So what are you going to do? You are going to tokenize as well as lowercase. So first lowercase and then first tokenize and then you can lowercase the tokens as well. Okay. So what I am going to do here is I am defining a function called tokenize that is going to take string, which is my text, as the input. Okay, and then I initialize an empty list because all my paragraph will be converted into a list of tokens. Clear enough? So I initialize an empty list called tokens, and also I am initializing there an empty string, 2 commas, okay, inverted commas, empty string called as word, wherein I will be accumulating the characters from a word. Try to understand, machine will not read the data word by word. It will read character by character. So first you have to figure out those characters, group them into word, try to understand where a new word is beginning, where the previous word is stopping, and then one word will be taken as one token. So you are doing those 2 processes simultaneously. That's why I am initializing one list wherein I will store my tokens of the words, okay, and one empty string wherein I will be collecting, reading character and collecting it as a word. Clear enough? Yeah. Now, next I am going to see for any boundaries. Why should I see boundary? Because I want to know whether the word is ending or not. So word will end with its boundary, like there should be a space or there should be a full stop. है ना? So what I am going to do, I am going to check if the character is a white space, like spaces, tabs, new lines, or punctuation marks like exclamatory mark, question mark, full stop, etc. And these characters will be considered as boundaries between the word. So what I am going to see, if any character in that particular string is white space. So I am going to use here a loop, and I am going to check string dot white space or string dot punctuation. So this is the beauty of now using the library of string. Okay, so string dot white space, string dot punctuation are we encountering anywhere in our given text data input. So if at all yes, then you know what you are going to do, you are going to append, the word is completed, you are going to append the word into the list of your word. Clear enough, guys? Yeah? See here. So if the word, if at all it has encountered the boundary, that is full stops or any white spaces, then it is going to be accumulating the word into its list of words as token. Okay, and it will reset the word variable again to be an empty string so that you can accumulate another word out of it. Clear? Now suppose if there is no boundary that is encountered, then that means what? The word is still not completed. You start appending the character. I think that is fair enough for you. Right? So if the character is not a boundary, then you add that to the word variable until a full word is getting accumulated. So now I think you are now able to read character by character, understand where the word is completing, filling that word into your token ka list. So do you have tokenized or not? So individually now you have got list of words which are serving as a token. So you can go ahead and just use tokens is equal to tokenize paragraph. Because we defined it as a function tokenize, now we are trying to implement that function over onto our text data. So text you are passing through your tokenize function and getting the output as your list of tokens. That was first thing. Then you want to avoid case sensitivity. For that reason you would be converting all the tokens that you have received so far in the tokens list into lowercase by using word dot lower. You will take that particular method, you will instantiate that particular method, and then you would convert all the tokens into lower cases. Clear enough? So you will be now printing actual tokens, you will be seeing the result in lower tokens. So when I print that, you can see the top one, you can see tokens, M is capital, machine. What was the sentence? Machine learning is fascinating, full stop. Text if you remember. See, machine learning is fascinating, full stop. It allows computer to learn from data. So now we have put it in the form of tokens. Machine before lowercasing, M is capital. Machine learning, comma, is fascinating, comma, it. So all spaces and boundaries of full stops are gone. You got all your proper tokens, but then what you are doing it dot lower instantiation, and you are converting all of them into lower tokens. So you can see downside, I have even printed lower tokens. So in this step, I have tokenized my text as well as I have converted that into lowercase. After you have converted that into lowercase, you are going to lemmatize this particular data. So what is lemmatization? All of you, it is very important in NLP task. Lemmatization is a process of reducing a word into its base form or root form, and that root is actually called as lemma. Okay? So you want to find lemma of a word, you will say. You will not say root word, you will say lemma of a particular text. Okay, that is lemmatization. Okay, so you will ensure that the resulting word belongs to the same linguistic category. Fascinating, fascinate. Okay, so example sentence here say leaves are falling off the trees. You would tokenize before lemmatization, it will be leaves are falling off trees. What would be lemma? Leaves, leaf. The root word is leaf. Plural is leaves. So what is the root word? Leaf. So leaves lemma is leaf. Are. Are means to be. Is. Are. You know. So I am writing the lemma as be. I am getting my lemma as be. Then falling. Fall. Ing is that continuous tense. We are not bothered. Root word. What is the lemma? Fall. Okay. Off is off. Trees is tree. Trees became tree. So that was all possible lemma that you could figure out. Clear enough? So now what will happen in your text? Lemmatization will happen. Wherever there are these words in your linguistic category, you will try to find lemma of it and replace it. Clear enough? So now what are we doing? We are defining another function called lemmatize. What would you lemmatize? Each token that you have arranged out of your paragraph, you would pass through this method of lemmatization and you would convert those words. So what am I writing here? Sorry. What am I writing here? I am writing, what is it? What is it? What am I declaring there? Dictionary. So I am storing all of them into a dictionary. Why? I have a key and a value. What is the key? Token. What is the value? Lemma. Everybody clear? Yeah. So now what I will get? I will give learning as my token, suppose, and lemma will be learn. So you have to give dictionary of lemma to it whenever you are doing lemmatization. You have to provide that. For lemmatization, you have to provide a dictionary. Yeah. As I told you, we are doing it from scratch. There are already inbuilt ones that you will invoke and use when you are going for a larger corpus. This is for your understanding, and yes, for your exercises, you will be creating based on the instructions given in the exercise. So here I have created 4 lemmas. Okay, learning became learn, computers lemma is computer, data lemma is datum, and networks lemma is network. So when you return these lemmatized tokens, you will store that into another particular list called lemmatized token and you will print that. So what changes could you find now into your tokens from the previous tokens to this? Those 4 lemmas that I have provided there, those root words are now reflected into the list of tokens. Clear enough? So what did we do? We tokenized, we lowercased, and now we have lemmatized. Clear enough? Next, we are going for stemming. So what is stemming? Stemming is the process of reducing a word to its root word or base form by removing any prefixes or suffixes, often without considering word's context or part of speech. So we are not bothered if it is a noun or a verb or whatsoever meaning it has got. All we are going to do is remove any sort of suffix or prefix. Fascinating. Remove ing. Fascinate. Understood? So that is stemming. Okay. So you remember our first sentence, no? What was it? Machine learning is fascinating. That was the first sentence of the so-called paragraph that we have just seen. So let's see this. I am defining here a method called stem wherein I am providing my tokens to it, and the suffixes again you will have to provide. Here we are giving from scratch. 3 suffixes I am giving here: ing, ed and s. Now you will see after you pass this on, after you perform stemming, your tokens will change. Okay. So what are we doing? You are taking a loop. You will check if your token ends with that suffix that you are given in the list. So what are you using there? Dot ends with. String library. Okay now? Tokens dot ends with whatever suffix list that you are providing. So in exercise you have to give your suffix list. Okay. And then you will return the token by removing suffix. Suffix means last part. Do your coding like that. Prefix may remove the first one. Suffix may remove the last part of that suffix. So the length of the suffix must be removed from that entire word. So that we are doing there while returning. You can see return token entire word range till minus length of the suffix. So suffix will be removed, word will be present. Clear enough? Clear enough with stemming, guys? Here I am doing only for suffix. Now, stemmed tokens, you will be storing that in a separate list after you do the for looping and take it out, and then you print it. So you can see here, what was the first sentence we had? Machine learning is fascinating. है ना? So what is the stemmed tokens that you have got? Machine ka machine, because there is no suffix in machine. है ना? Next is learning was there. Learning, there was a suffix. ing is mentioned now. So learning became learn. Is mein se you can see s is gone, because there I have given actually s. Correct. And then fascinating, ing is gone. Check there. Fascinate, spelling is wrong. I am not bothered it is verb, whether it is noun. Only thing we are bothered is the root word. Understood? So that's how stemming is done. Try to understand the beauty. That's the reason I am telling these. Again, fascinate where there is no E. No? You purify that later. Okay. Clear enough, guys? Yeah. Now, next is what? Reviews ka example I told, no? You will only scan for keywords. Irrelevant words you just discard. How you are doing that? Using stop words removal. So this is again a pre-processing part. You remove this and pass only keywords via tokenizing, via lemmatizing, via stemming to your LSTM model as vector, and then it does its neural network part. Clear enough, right? So this is just like an wrapper over an LSTM model. This wrapper is very important to design, and the hyperparameter there will be the vector length that you would be choosing. Clear enough? Right. So stop words are commonly used words in natural language that are usually filtered out in NLP tasks because they carry little to no information distinctively. These words serve a grammatical purpose but do not significantly contribute to the understanding or to the context of your text. Some example, a, the, an, is, was, etc. Clear? Now, what are we doing in the code? We have to give our set of stop words. You have to decide your stop words and give that to the machine. Everything has to be trained. It cannot do anything on its own. You are going to give, right? So you are giving a set of words that are actually stop words that could be ignored, and then you will be looping that and finding it out if they are present in your tokens. If it is there, then you would be simply discarding them off. And after that, what you get will be your filtered tokens. So what was our first sentence? Machine learning is fascinating. So what you got here? I is still there because after stemming we are doing it. So you can see the R, the, all those things got filtered out in this filtered tokens. Are you clear? So these are filtered tokens after you have removed any sort of stop words that you have given the machine. Okay? So how did we begin? We gave the data. What was the first step? What was the first step? Tokenization. What was the next step? Lower casing. Why? To avoid case sensitivity. Then lemmatization. What does it do? To extract the root word. Correct. Then stemming. What does it do? Remove any prefixes or suffixes. Then stop words. What do you mean by stop word? Insignificant word in a natural language that can be removed without affecting the meaning or context of your text. Okay? These processes are clear enough? Yes. Next important part now. What is it? Embedding. So all of these things come under an embedding layer, which is like a wrapper over of your RNN model or an LSTM model. After you pass through this block of embedding, you will go through another neural network block, which could be either a RNN or an LSTM. Clear enough? So now what is happening in embedding now? As I told you, machine cannot understand words or characters or strings. It can understand only numerical values, for which here, for higher amount of computation, tensors. Simplest form of tensor is a vector. Clear enough, guys? So here, word to vector embedding. You are embedding a word given in a particular text or an input into a vector form suitable enough to understand by the machine. Irrelevant information is stopped. Okay, only root words are extracted so that you can predict better. All punctuations, white spaces, everything discarded. Only relevant information is taken, lemmatized, stemmed, lowercased, tokenized, and then converted. Sorry, I'm telling in a different order. It should be tokenized, lowercased, lemmatized, stemmed, stop words to be removed, and then it will be ready for converting into a lookup table of vectors, which we call embedding matrix, which I explained you today in the class. What is the size of embedding matrix? Don't tell 10,000 by 100, it was just an example. Vocabulary size means number of words. Number of words means number of tokens. So indexing token is important or not? Yes or no? So here we will see how we will index a particular token. Okay. So define create word vector is the method that I have chosen here. I am giving input as what? Tokens. Okay. Tokens I am giving my input. Apart from token, very important thing that I am passing there, dimension of the vector. So that is user specific. Again I am telling. How big you are taking vectors, that many words you can actually, you know, accommodate. But that much you have to pay for the computation. That much you have to see. Few applications are worth enough. Worth enough. So you give proper good amount of vector dimension, weight enough so that you get accurate value, where accuracy matters. Speed and time can take a little trade-off. So based on application to application, you have to select that size of vector, dimension of the vector. Clear enough? So here I am choosing vector size as 50. Now I am using simplistic word vector creation. There I am using a method called set. What does set do? Creates unique words for me, for us. That means any repetitions are present in those tokens will be discarded. Only unique tokens will be retained. Okay. So set method will, you know, refine your tokens to unique tokens and then give it back into a list called vocab. And then what are you going to do? You are going to initialize, you are going to actually assign a vector to this word is now to, you know, convert that word to a vector. I told you there are two ways, do you remember? When I explained you embeddings today in the first session, I told you there are two ways in which you can provide vectors to words.
Vector to word and word to.
One is by doing it on your own by random initialization, remember? One is through pre-trained vectors. If you are going for a larger corpus, better go for pre-trained vectors. Since you are learning the concept, we'll do it from scratch. So what I am doing here, I am randomly initializing vectors for my words. Okay, so what am I doing there? Can you see? Word vectors is equal to word is taken as what? Torch dot random of word vector size. So a random vector is generated using RAND method using its parameter as the dimension that you have chosen. So here I have chosen what as my dimension? 50. So a length of 50 vector randomly will be produced using PyTorch, and it will be assigned to all the tokens that are present throughout, unique tokens that are present throughout. Clear enough? This is how a word is converted into a vector. Are you clear, everybody? Right. So you are going to return the word vectors that you generate after randomly creating a vector, you know, the vector of length 50 for every individual word that you come across in your token, and then you return the word vector through these filtered tokens. After that, I also require indices to these particular tokens. So I have to provide index for my token. So what I am going to do, assign word indices. So for this I am using an enumerate method so that I can provide an index to my token, to my word vector that is generated to my token. Okay, so you have now generated an index as well for your particular word. Clear enough? Right. So you can see here when I print this word to index, what am I getting? Machine. Machine is giving me what index? 17. Learn 23. I 48. Like that you have now indexed each and every tokens. This is word to index. If you want, you can also go for index to word as well. We'll just zoom it a bit so that you can understand. Yes. Is it clear, guys? Clear enough? Yeah? Can you see the output? What did we get? For all those tokens that were unique in nature, you have created the vectors that will be internally going to your neural network model. Okay? And you will index it for your personal references that you can print and you can check. Clear enough? This is word to index, and the next slide will be indexed to word. Okay, word comes first, index later, word to index, index come first, word later, index to word. So this was all about text pre-processing and embedding. So now from here, mathematical calculation starts. You take these vectors and pass this on as an input to whom? To an NN model. It could be an RNN, it could be an LSTM, it could be a GRU. Basically any sequential learning model, the wrapper part is text pre-processing and embedding. You take it, you get vectors out of it after proper pre-processing of lemmatization, stemming, etc., etc. Take those vectors, either generate them randomly from scratch or use pre-trained vectors. Basically, take those vectors, pass it to any sequential neural network like RNN, LSTM, GRU.